So we got buffers. Buffer in everyday life usually means some kind of protective thing. Like the desk was scraping across the floor when I moved it, so I put buffers underneath the legs. Buffers are protective layers, and what the buffers we're going to learn about here protect against is pH change. The important thing to remember about what a buffer is, it's a weak acid-base pair. Not strong acids, they can't do it. All they want to do is ionize and they won't help out at all. Weak acid-base pairs tend to be not all dissolved in solution. They are not strong electrolytes. Some of them will be in the undissociated form, so you're able to pull protons out of solution. You're able to make water. And by doing that, you can resist pH change by using the correct buffer. So what happens here? We make a buffer that's a weak acid and its conjugate base. So what I would start with to make this buffer that's going to do this thing, I would start with, let's say I want acetic acid. And that's the example in your packet. If I want acetic acid to be my weak acid, what I need to combine it with is this side. My source of protons, which would be the acetic acid, and my source of its anion, which would be, take the H off, the acetate ion. So from acetic acid, take off the proton, it's the acetate ion. I need to then find a source of the acetate ion. What's usually used is a group 1 metal with that thing, because those will always dissociate. Group 1, always soluble. I use sodium. I just think of sodium. So, sodium acetate, which I have it typed out there not the cool way. If you combine the O's, it's nacho, which is also cool. So what you need to do to start making buffers is weak acid and its conjugate base. How do I do that? Basically replace one hydrogen with one sodium. That's the hack on this. That's really easy. So I've gotten this side where this would be sodium acetate, or this would be acetic acid, and this would represent the ionized sodium acetate, C2H3O2 minus, my weak acid base pair. So what I do then is I'm looking and I'm seeing some information down here at the bottom talking about which way I would shift my equilibrium from this. That's nice. It's not the most practical thing to talk about. This is probably a better way to look at where adding H and adding OH, what they're going to do. So if I were to add a strong acid to this system, it would pick up, it would break down. I used HCl. We're going to ionize to H plus and Cl and make it acidic because of the presence of H plus. Nah. My anion combines with it, takes the H plus, takes the protons out of solution, and gives you neutralization of the pH. It's going to change the pH a little, and that's the equilibrium shift. If I add a strong base, because there's my adding of OH, again, I have the protons from the breakdown of acetic acid. I have protons to combine with OH and give me a neutral pH with sodium cation and water. Either way, this side of the equation will react with an acid or a base. A small amount. You can't straight dump it and expect it to survive. Buffers have a limited capacity that depends on what acid's used and their volume. So this reaction, though, sort of sponges up small amounts of strong acid and strong base. That's important. And I love this equation. This is called the Henderson-Hasselbalch equation. I don't remember learning it in Gen Chem. I learned it in biochem because we were talking about the carbonate buffer system in the body. Easy to use. Super easy equation to use. You need a Ka value. Take the negative log of your Ka to get to pKa. Regular old log, not Ln. Base over concentration of base over concentration of acid. So easy to use. Your book shows examples of these calculations doing common ion effect with an ice chart. Takes about 5 times as long for me. And when I was doing the homework for this chapter, I just straight up Henderson-Hasselbalch, like 2 pages of it. Let's look at the example. I was trying to highlight acid in pink and base in blue so that you could see how I would denote them. There's acetic acid, COOH, has the hydrogen. Sodium acetate, the formula isn't given, but what you should know is when you see acetate, take off the H and make it minus. If I were to have you write that formula, it would be nacho, NaC2H3O2. You're good. If you want to write it, one more thing, if you want to write it ionized, which it would be, sodium would make it a strong electrolyte, you can just write it as the acetate ion also, and you'll see that. I was trying to cover everything you could see in terms of how it's written, because the problems in your chapter sort of throw that at you without telling you, oh, this is what it means. So all I wanted to do was my concentration of base over concentration of acid. They also don't make a big deal out of this, but if I were to give you moles of base and moles of acid, they're in the same solution. They're mixed together. So they would have the same volume. Volume would cancel, and you can just use moles as well. There are definitely some examples of that. All I did was throw in 60 over 10, take the log. What's cool is what's cool is you can tell from the log if the pH is going to go up or down. We're going to look at that with additions next time. You'll be able to predict because the log will come up as either positive or negative to help you with the pH change. Negative log of 1.8 times 10 to the negative fifth is my pKa, plus the answer from my fraction in the log gives me a pH for this buffer of 5.52. Buffer capacity is how much you can add. It's going to be determined by, again, volume and other properties of the buffer that result from the acid-base pair, namely your pKa. We've got a pH range. Buffers don't work all the time. You can't just magically pick a set of buffers for a pH range you want. It's going to be determined by pKa. So that's a take-home fact. Your pKa of the acid you use determines whether a buffer will be effective in a certain pH range. So if you check it out, buffers are most effective, this is good to know, when the concentrations of weak acid and weak base are equal, because it cancels out that log term and makes pH equal pKa, which is 2 thumbs up perfect. That's what you want. This pH gives the optimal range of a buffer. You can use a buffer in the range of +1, -1 pH units of pKa. The closer, the better. So, wow, I want a pH of 4.8. Acetic acid gives me 4.74. Bien. Wonderful. And that's what you got to do there. You're using the Henderson-Hasselbalch equation in your calculations today, but you had a lot of take-home messages from that of little facts. So read through these notes and practice your calculations.